Hello everyone, welcome you all. Today I will discuss a topological problem which was asked in Tifr exam. The problem is there exists a complete metric on the open interval 0, 1 inducing the usual topology. It is a true and false question. So is it true or false that there exists a complete metric on the open interval 0, 1 which will induce the usual topology on open interval 0, 1? The usual topology on open interval 0, 1 is the subspace topology. So how can we do this? First of all, it is true. Yes, there exists a complete metric on the open interval 0, 1 which will induce the usual topology. So first, in step 1, we need to define a homeomorphism. First, define a map F from open interval 0, 1 to R as f of x 10 pi time x minus 1 by 2. See, the graph of this map is at x tending to 0 from negative side, f of x is tending to minus infinity, and when x tends to 1, then f of x tending to plus infinity, and at x equal to 1 by 2, f of x is 0. Clearly, this map f is continuous and bijective. So, the inverse of f will be, let's say f of x equal to y, then this implies that tan of pi time x minus 1 by 2 is y. This will implies pi time x minus 1 by 2 is tan inverse of y. This will imply that 1 by 2 plus 1 by 5 time tan inverse of y. So the inverse of f will be f inverse from R to open interval 0, 1 defined as 1 by 5 time tan inverse of x. This, clearly it is also continuous, so f is homeomorphism. In step 2, define a metric T from open interval 0, 1 in open interval 0, 1 as this. See, if a map F defined on the space X is injective, then D has defined as d of x comma y modulus of f of x minus f of y. Then this define a metric on x. This is a important result in function analysis. So the metric T is a metric on open interval 0, 1. See, this is the difference between 2 points in R. So it is a usual metric on R. That's why it will induce a usual topology on R, because the usual metric on R induce the usual topology on R. Now we need to show that this metric T is a complete metric. We know that a metric space is a complete metric space if any Cauchy sequence xn in that metric space is convergent. Then we say that the metric space is a complete. So let's take an arbitrary Cauchy sequence xn in the metric space 0, 1 D. This is a Cauchy sequence. That means d of xn xm will be less than f sign for some f sign greater than 0 and n or m greater than some integer n. Since d of xn xm is modulus of f of xn minus f of xm less than epsilon. This implies the sequence f of xn is Cauchy in R. And since R is a complete metric space, so every Cauchy sequence is convergent. That means f of xn will converge to some point y in R. Now we will use the continuity of f inverse. F inverse is continuous, so f inverse of f of xn, which is xn, will converge to f inverse of y. This belongs to open interval 0 1. So we have taken an arbitrary Cauchy sequence xn here, and here we have showed that xn is convergent in open interval 0 1. So that means every Cauchy sequence is convergent in this metric space. So the metric space open interval 0 1 d is complete. And since it induces the usual topology on R, so it will induce the usual topology on open interval 0 1, that is subspace topology. So the given statement is true. Yes, there exists a complete metric on the open interval 0 1 which will induce the usual topology on open interval 0 1. Thank you for watching.